Without further ado, let me introduce our first speaker. Craig McNeile from the University of Plymouth is a theoretical physicist. Did I get that right? That's right. Theoretical physicist working in particle physics, where you're by necessity having to work with huge amounts of data, and I hope we'll get to hear about how you do that. So let's welcome Craig.
Okay, so the way I've kind of structured the talk, I'm going to give you a very broad overview of particle physics and some of the kind of issues we're facing. And my kind of expertise is something called QCD, the way the quarks and gluons interact, and we use high-performance computers, holds a lot of data. So the first part talks in a very broad overview of particle physics, and the second part is sort of how we use computing and how sort of data arises for a particle physics application. And so the particle physics stuff is going to be very, very gentle. I put in slightly more technical details, not too much technical details, because of your background, than I would for a general audience. But there's going to be nothing too hard. Okay, so what is particle physics? Well, the aim of particle physics is to determine the fundamental particles and the interactions between them. So, for example, in the past, people thought the proton was an elementary particle. Proton is one of the basic things that builds nucleuses. As we looked at smaller and smaller distance scales, we found that proton is actually not an elementary particle. It's made of quarks and gluons. And so we begin to know more about the universe. The standard model of particle physics describes the interaction of all known particles. And also, in the past, people saw electricity, magnetism, they were separate things. Turns out they're sort of different aspects of the same theory. So one of the underlying themes of particle physics is unification. Can we take all these different theories, and actually they're just sort of different aspects of the same theory. And even the latest ideas that radioactivity is also kind of unified. So the standard model of particle physics was completed by the discovery of the Higgs boson a couple of years ago. I'm not going to talk too much about that. We'll talk about the LHC. The theory is well tested. So that's sort of the good news. Where things go down a little bit, so we'll try and take this a bit further. So I've told you we have quarks and gluons. We want to know more about quarks and gluons, and can we sort of, if quarks have masses, can we actually find out why the quarks have certain masses? Okay, so one of the things they noticed is, so here's a picture of a galaxy. You can kind of do Newton's laws if you solve the same way you can solve trajectories of planets in the solar systems. You can work out how fast they should be going to the amount of matter. And here's the kind of rotation curve. So this is the distance out to the galaxy. Here's the galaxy go further out. And here's the velocity of the star. So you look at a star, you can work out what the velocity is. And that's the kind of prediction, and then that's what's observed. And the two things are very different. And the observed also assumes that most of the matter is kind of stars, and it's luminous, you can see what's there. To kind of move the theory up to the experiment, people introduce this idea of dark matter, which is just some particles that don't really couple to matter, that don't couple to light, but have gravitational interactions. And okay, fine. But then, so we see this in astronomy. What we want to do is have a theory of what this dark matter is, and that's part of the idea of particle physics. Somehow things get worse. So I'm not really going to give you the evidence, but there's something else called dark energy. What people is they're trying to determine the amount of mass and energy in the universe. There's two ways of looking at that. One of which you can look at supernova, and you can tell, using the Doppler effect, how fast they're moving, and you can tell how far they're away. And when you kind of model that, and also there's something called the cosmic microwave background radiation. These are photons from the Big Bang. And when people look in the fluctuations of that, when they fit this to cosmological models, they find, to explain the acceleration of gravity, is you need this thing called dark energy. It used to be called something the cosmological constant. we don't really know what it is. I mean, even the fact it's called dark energy is sort of a bad thing. It's sort of so the bottom line is we only understand 5% of the energy in the universe. So as a particle physicist, I should at least understand more than 5% of the energy in the universe. Okay, so we want to do something like we did with the protons. The proton is made out of quarks and muons. We want to find some elementary particles that explain at least the dark matter, and in an ideal world, the dark energy as well. So how do we do that experiment? Einstein told us that E equals mc squared. You can convert mass into energy. So the most simple particles experiment is you batch two particles together, convert it into energy, and from the energy you can create new particles. And perhaps in an ideal world, the new particles would be the particle that explains the dark matter, the stuff we don't know. So that would be the goal, and somebody get the Nobel Prize. Fortunately not me, but that would be kind of cool. Unfortunately, depending on, we don't know how heavy these particles of the dark matter are, so you have to batch the particles together at higher and higher energy. That costs more money. We'll see how much more money later. And that's a sort of standard paradigm of particle physics experiments. This is a very broad treatment. There are also experiments in mines trying to directly detect the dark matter. But I'm not really going to talk about that. They're also not, I'll talk about the conclusions later. Okay, so the main particle accelerator in the world at the moment is at CERN. It's roughly 20 member states. Don't worry, it's not actually part of the EU. The total cost of building the LHC, Large Hadron Collider, which I'll show in a bit, was about sort of 4 billion. Very cheap. And there's been a long history of particle physics at CERN. They started it in 1951. There was the accelerator in 1974 that they got Nobel Prizes. In 1983, the W Zs, the particles important for radioactivity. There was another accelerator called LEP, which is electrons and anti-electrons, and then the LHC started in kind of 2008. And these three things have given us the experimental evidence of what the standard model of particle physics is. And I should say, actually, one of the professors I knew at Liverpool said actually when they started CERN off, the original part of the experiments were in Liverpool, actually under where the Catholic Cathedral is. That was their first kind of experimental ring in the early 50s. Okay, so here's the Large Hadron Collider. So the motivation was it's a ring between Switzerland and France. The main goal is to find something called the Higgs boson. I'm not going to talk about too much. But now what they're really trying to do is to find, I mean, they'd be super happy if they could find this particle that is dark matter. And I should say, roughly, they're interested in colliding kind of nuclei, because you can study the origins of part of the Big Bang, and they do that for 1 month a year. Okay, so what they do in the LHC is they collide protons together. So this is the E equals mc squared. You've got to remember the proton is made out of quarks, so you don't get all the energy of the protons. And it is a bit of a mess. We'll see some pictures a bit later. So you collide them together, you get some particles coming out, and you're looking for something you don't understand. Or somebody proposes some theory, and they're looking for some kind of picture or some kind of new kind of particle. But the basic idea is E equals mc squared, batch particles together, create some energy, look for new particles, or some physics you don't understand. Okay, so a detector just means they batch particles together there, and then they compute the energy, curve particles in the magnetic field, and they can determine the energy and various things. There's two general purpose experiments, CMS and Atlas. 2 is kind of an important number because occasionally you'll see experimental results. Last week somebody was claiming from Hungary claiming a new particle, but the problem is it comes from one experiment, and really you need a couple of experiments where all the systematic errors are done differently to make sure that what he's seeing is a real effect. So that's just the way it is. So, I mean, somebody told me when they were doing the funding for the UK, they said, well, why is it 2 experiments? Why don't you just have 1 experiment? And you do need a cross-check. Otherwise, you could be kind of fooling yourself. The LHC I'll talk about a bit about at the end. So these kind of collisions are very, very messy. You bash particles together, and you get all these lines out. Particle physics have always used a lot of statistics. Now, increasingly, they're using machine learning a lot because they're trying to move from these kind of tracks. You see here, you have 2 protons colliding and all these track to charged particles, and they're trying to reconstruct what the elementary particles are. And the last conference I went to, I mean, maybe 70% of the particle physics talks, experimental talks, were using different machine learning algorithms to move between the picture of all these kind of collisions into some kind of insightful information about the underlying physics. And ultimately, you're trying to look for some rare event that is this new dark matter particle. Okay, so our funding body in the UK for particle physics is called the Science, Technology and Facilities Council, and they have a bunch of questions. What are the fundamental particles? What is the nature of space-time? Is there a unified framework? I told you we've got a long way from electricity and magnetism to be unified, some radiation. Can we take this unified theory further? So everything, all physics is just one unified theory. And then what is the nature of dark matter? What is the nature of dark energy? So when you write a grant application, you say, this is what I'm trying to do, because it somehow defines how the kind of questions they thought were important. I mean, okay, so that's what we're trying to do. What's the status report? So people have various, so we have this idea of dark matter, so you want to have some kind of underlying theory that kind of explains it. It's not just some particle, there should be some kind of interaction, some equations, right? It's physics. There should be some equations to explain this. Some of the popular things are supersymmetry. This is very popular in the theory community. Not by me, I personally hate it, but and then something called Technicolor, which is modelled on the ideas of looking at quarks and gluons, how you make protons, doing something similar to that, and building elementary particle theories. Some of my colleagues at Plymouth University work on this, using kind of supercomputers to explore different theories, to try and develop theories of what dark matter is and the interactions. So what is supersymmetry? So here are all the parameters that of the standard model. These parts we know. These things here are quarks, up, down, chance range, top, bottom. Up and down are the ones that make up nuclear physics. Here is the neutrinos, the electrons, important for electronics. We'll talk about this one later on in Muon. And then these things, this is important for radiation, the gluons are important for kind of nuclear physics, and the gamma is the photon, important for radiation, that's providing all the light in the room. Supersymmetry takes a direct copy of that. It's sort of a generalization of general relativity to the symmetry, and it just kind of copies all these particles over. So there is a symmetry. The symmetry is kind of technically broken because we don't see all of these things, so somehow they have to increase the masses in some kind of way. And actually the new theories have a lot of unknown parameters. And then some combination, they believe some combination of these particles down here. So we have quarks and gluons, and in supersymmetry you have gluinos and stuff like that. Have all these new names, lots of particles. And I believe some of these particles are good, in principle, good candidates for what dark matter is. The slight problem is we don't really know what the masses of these particles are. There were some kind of ideas, but they were kind of speculations. Well, theorists before, they said it's very unlikely this to be wrong, but we'll see later if they were wrong. CZ is an important part of something called string theory. Well, I'm not going to hype them anymore. They do themselves. So how's we going experimentally? So I just want to stress that the LHC has made a lot of important experiments. They write a huge number of papers. You know, lots of men are going fantastically. The downside is they found no new interactions or no new particles. So they still haven't found this particle with dark matter. And so what can go wrong? Well, as I said, the supersymmetry particles just could be too heavy. The LHC, we have a certain energy, you batch particles together, and if you don't have enough energy, you can't create these new particles. So, there are theoretical reasons, and so essentially you say, well, maybe the SUSY particles should be made a bit heavier. And because particle physics is a bit more complicated than that, but essentially just make the particles a bit more heavier. Unfortunately, they've actually said this. I told you at the beginning that at CERN they had a collider called the SPS. They claimed that they were almost guaranteed to find supersymmetry there. They didn't find them. They claimed at the LEP, almost guaranteed to find supersymmetry particles. They didn't find them there. There was a collider in the US called the Tevatron, almost guaranteed to find supersymmetry particles. Didn't find them there. You kind of see there's a like pattern emerging. So it's still possible. I mean, a lot of the senior people think it's still very possible. If they build another collider, they will find the supersymmetric particles. But it's very difficult to plan a new experiment because you say how much energy you're going to collide particles together, and you say, well, if we're going to give you this amount of money, what particles are you going to discover? And you can say, well, Okay, so there's another kind of way of doing this. This is based on kind of quantum mechanics. So in normal days, everyday life, we can specify the energy of particle and the time. In quantum mechanics, there's a bit of fuzziness, uncertainty, and one of the uncertainty relationship is that there's an uncertainty on the energy of a particle and the time. So there's a little kind of error on these things. An uncertainty on the time, and there's an inequality that this thing has to be greater than h by 4 pi. H is a very small number called the Planck's constant, and this is just part of quantum mechanics. It's one of the kind of weird things of particle physics. This thing excludes because this is such a small number, we don't see this in normal physics, in normal kind of classical physics, but it's been sort of well tested at an experiment. Okay, so the way we deal with so because we're dealing with things like the creation of particles, the quantum field theory, so quantum mechanics, essentially the number of particles are the same. If you want to create particles, destroy particles, you have to do something called quantum field theory that just built to create and destroy particles. There's a kind of bookkeeping device to keep track of these things called Feynman diagrams. So here's an electron, positron, positron sort of an anti-electron, emits a photon, and then it creates a quark and anti-quark, and a little gluon coming off. It's a kind of bookkeeping device. This thing's related to essentially an integral, and there's a way of doing kind of calculations of these things. And the way the kind of time energy uncertainty principle is sort of tied up in this. But the bottom line is you can another way of getting high energies, remember to find this dark matter, we want to go to higher energies. Because of this energy uncertainty relationship, for small periods of time, we can create higher energy particles. And in these Feynman diagrams, and they will affect the properties of particles we do know. So essentially, if we accurately study the properties of known particles, like their masses, various amplitudes, if there's a deviation between the known physics, this could be the fact that we're missing off the physics of some unknown particle, and that could be the evidence for what the scale of this new physics is, or the start of this mapping out new beyond the standard model physics. Okay, and that's the kind of approach we're going to take. With my supercomputer calculations, we're going to do very accurate calculations just within a standard model, look for deviations, and then we can try and hopefully find out what the dark matter is. Okay, and this has been done a long time. So before the Higgs boson was discovered, there are very weak constraints on its mass for various technical reasons, but it has been used a number of times in particle physics to use these virtual corrections, which a particle just popping into existence with much higher energy than your kind of things you're bashing the energy with, and you kind of probe higher energy scales using this virtual thing. So it's not a new technique, it's quite a basic technique. The bottom line is you need to do very precise calculations of your known theories. Okay, so I'm going to tell you about one experiment. This is going to be like a case study. There's a number of different places where to do this, one of which is to do with the muon. The muon is essentially, so we have electrons, it forces electric currents to flow. The muon is essentially a copy of the electron. It's about 200 times heavier. It is slightly different in fact because it's unstable, it does decay. When it was first discovered experimentally, somebody said, well, who ordered that? What's the point of it? And it just turns out in particle physics, we have up and down quarks, we had a family of particles, and then we got another copy of them, we don't know why, and then another copy of them, and we don't know why, and then after that we think there's no more than that, and we don't know why that is either. So. But, you know, I have faith. One day we may find this. So the actual experiment I'm going to talk about is experiment in the States. The magnetic moment of the muon governs the interaction with the magnetic field. So this is something I'm going to, in my supercomputer calculations, we're going to kind of compute a contribution to that. And also virtual particles contribute to that. So this is going to be one of our things where there could be that some particles of a new theory pop out of the vacuum and contribute to this thing. Okay, there's going to be new experiments, so I'll tell you a little bit about experiments, but just remember, so here are the kind of diagrams. Here's the muon, here's the photon coming out, and this is the interaction of this muon, this heavy electron with magnetic field. There's little squiggly things, lots of particles contributing. The thing I'm going to be interested in here is there's little photons, they turn into kind of QCD type things, quarks and gluons. This is the thing that, well, frankly, it's the only thing I can do. And this is my kind of research piece to do this thing. This little bit here is important for computing the standard model prediction. Up at the top, to look for virtual corrections, we have experiment, and then we have the standard model theory. A couple of things to note about this. So there's two errors, one from experiment and one from theory. This 10 to the minus 11. This is like 0.0, about 10 zeros and 1 1. It's a very, very small number. The actual standard model calculation is very accurate. It's one of the most accurate numbers we know. So there's error bars from the theory. Error bars just from experiment. Experiments have error bars. Experiment doesn't have an error bar. It's probably a bit dodgy, really. This 3.6 sigma. So there's kind of, with errors, there's some kind of fluctuation in it. And if you have a deviation between theory and experiment, if the sometimes that just could be from chance. There's some kind of randomness in the nature of errors. So this kind of 3.6 deviation, in particle physics, we start to get excited by that. You don't get a Nobel Prize, but you get like, you start to get excited. Unfortunately, if you're designing drugs, you get your drugs approved at sort of 2 sigma. That's why some of these things are really problematic. But really, to get a Nobel Prize, you need this thing to be 5 sigma. That means the experiments need to reduce their errors, and the theorists also need to reduce their errors. And so, this is the idea, right? If we compute very accurately, the theory we already have, we can hopefully find a deviation, and that will give us some information about dark matter. Okay, so I'm going to tell you, so there's a new experiment. So I'm involved in some of the theory calculations. It's a small experiment, only 200 people in it. That's small for particle physics. 7 countries. There's some UK involvement. One of my theory colleagues, somebody I shared an office with at Liverpool, was a theorist, but now he's part of the experimental collaboration. They're going to result new results next year. And so the last result we looked at was from an old calculation at Brookhaven. This is a lab in the US. I think the old result is maybe 10 years. Now they're going to do, they're doing a new experiment at Fermilab, which is an experiment in Indiana. And so in 2-3 years, I think they're going to reduce the error bars by a factor of 4. And so that could help us. If theory errors go down, that could help us move beyond this 5 sigma. Or it will just go away, and I'll have wasted 3 years of my life. Okay, so actually, I told you the Muon experiment is the interaction of the muon with the magnetic field. So actually, they have a big magnet. When they rebuilt the experiment, there was they had to move it from Brookhaven. They decided to just reuse the magnet. So here it was so big, they had to move. They moved some of it by barge from Long Island to Indiana, and here it's just coming up to the lab. It's a huge magnet. So you could actually trace it on Facebook and things like that as they move this big magnet around. I thought actually, since the next talk is on magnets, I should actually find out something about the magnet, like why they're using it. 1.5 Teslas, that's a measure of how strong the magnetic field is. It's superconducting, so it's a strong magnetic field. I think the key thing they liked about it, they wanted a very even magnetic field for their experiments. So they claimed something like 70 parts per billion. So this is the thing that experimenters do. And yeah. Okay, so one of the main errors in this thing is from QCD. QCD is the theory of quarks and gluons. The proton is the main thing that makes up our bodies. It's made from quarks and gluon. And QCD, quantum chromodynamics, describes the interactions of quarks and gluons. Okay, so this is, so as part of that deviation, we have to do a kind of calculation. And one way to do these kind of calculations, you essentially have to do, well, one way of doing this is to use a big supercomputer. One way to do quantum mechanics is to do something called the path integral. Equation doesn't really matter. What it is, essentially, you integrate all over all possible values of the fields, and the interactions are here, this kind of weights them. So this thing is called the path integral, it's invented by Feynman. This thing here is, the way it works is, I create a row over here, a row Muon, made out of quarks, antiquarks, it propagates for a bit, and then I destroy it. And that's the fundamental interaction we use, and that's what these things do here. The essential idea is you integrate over all possible fields. That's kind of the way that Feynman told us to do quantum mechanics. Okay, the trouble is, this is an infinite dimensional integral. Infinity is always difficult to deal with, so we regulate it as a fancy word is we introduce a space-time lattice, introduce some points everywhere. That converts this thing into a big integral, which is hard to solve, but at least it's similar to other things. And what we do is use something called the Monte Carlo method, just means lots of random numbers. And also we use analogies with statistical systems, but the Monte Carlo method is essentially using lots of random numbers. Yeah, and one of the key things, one of the ways the random numbers works is we create kind of snapshots of the vacuum, just because you use random numbers, and the way the dynamics works is you get a kind of snapshot of the QCD vacuum, and that's sort of the basis of our calculation. And it's also the key data. When I talk about the computational stuff, that's the thing that is most expensive to create, and the most useful. Okay, so we had an infinite dimensional. Feynman told us this path integral. The integrals are infinite dimensional. We regulate it by introducing a space-time lattice. The slight problem with that is the real world doesn't have a lattice. So what we have to do is we have to do the calculations a number of different times with different volumes, different lattice spacings, and then we do like an extrapolation to the infinite volume limit and also to the continuum limit. That also has implications for data handling because I have to repeat my calculations multiple times, and I have data tagged by different lattice spacings, different volumes. Okay, and just this is the only thing I want to tell you about the algorithm. kind of the key step, at least when I do the calculations I do, one of the key things we have is a quark propagator. This tells us how a quark propagates from here over to here. If you met before something called a matrix, that's essentially what we're solving. The matrix equation mx equals b. We put b down, m's the theory that's told, and x is the thing we want to solve for. And these are big matrices of order more than 1 million, 10 million. Okay, and then once we have these x's, we can combine them together to do mesons and stuff like that. But one of the key underlying kernels is matrix inversions. And we use things like conjugate gradient, increasingly things like multigrid. If you've ever met any of these things, it doesn't really matter, but it's mostly kind of matrix algebra. And then, remember, we're doing Monte Carlo. That means we have random samples. So every time we do a calculation, I have lots of random numbers, and I just keep repeating the calculation, and then I do some statistics at the end. Okay, so when I talk to the computing stuff, there's a couple of different parts of the calculation, one of which is on supercomputers. This is to do my matrix inversions, generate my snapshots of the vacuum. What I get out of it doesn't really matter too much. This is the correlator. This tells me row here, create a row here, destroy a row later, and you end up with some kind of data. This is a log scale. This is distance to Fermi. But at this stage, this is something you fit, right? If you've done fitting a straight line or chi-square, these things are actually exponentials. So we have to use log over chi-square minimization. But at this stage, so there's a supercomputer stage. When we get graphs like this, it's Python time, right? And so some people use R. I've used C++ in the past. There's no book called numerical recipes, but most of us learn to overcome numerical analysis techniques. And then we use a technique called bootstrap to do the errors, just the way these things work. And one of the issues, just a point, one of the issues here is these things are very, very noisy. And one of the problems with the calculations, we want to reduce the errors on these large time points. And we're going to have to be a bit more clever to do that. Okay, so just so does this all work? So quarks and anti-quarks form of particles called mesons. There's experiments. So this plot just shows the different mesons. There's charm quarks and anti-charm quarks. So the red line's experiment, and then my collaborators have computed the masses of various particles. Okay, so these are the red lines are sort of different experimental masses, and then the circles are the results from the lattice calculations. Some particles we have to use, some things we have to input to the calculation, like what the quark masses are. So some particles are input to the calculation, and then some things are predictions. So this is a comparison against theory and experiment, and the fact that all these things line up shows you what we're not doing is not crazy, it's working reasonably well. Okay, so that's the kind of physics. Now we're going to do some hacking, a little bit anyway. So, because the data is so big, we have to usually use parallel computers. This is not a great plot I pulled off something else. So essentially, we run on parallel computers. It means we might run with 2,000 nodes, 2,000 PCs. So I have a lattice, and I put part of my lattice on one of the PCs, on one of the nodes, another part on another lattice, and that's sort of the way the high-performance computing works. And then sometimes I need, when I do my calculations, I need information here, and there's a little bit of kind of communication. So it's a kind of high-performance computing idea. This is the way it works. You distribute your lattice of the different nodes, and then there's some kind of communications to work. For some applications, this doesn't work very well. For this QC application, the parallelization works very well, and you can use lots and lots of cores, sort of 2,000 or more. Some groups have their own codes to do these things. So these are all the supercomputer codes, and one time I had to sign an NDA for one code, which was, okay, that's fine. There are some kind of open source codes. This is an old code written in C. Chrome is written in C++, Grid's written in C++. performance is really critical in these things. Some of the computation-intensive parts are written in assembler. There are some people who actually just spend their time tuning these things. When we see the cost of a supercomputer, in the US, a big supercomputer is like $100 million. And if you say my code's only 5% efficient, you're wasting kind of money, really. So they like to see some attempts at efficiency. 38% is outstanding. People have a lot of experience with doing these different things. So there's people who've done this for years and years. They kind of know what they're doing. I'm not an expert on that tuning so much. Another important issue is portability, because if you want to get very high efficiency of your code, different computers have different architectures. And one of the issues is if you're working on different types of computers from different vendors, the way you get efficiency will be very, very different. And sometimes you can use, so you need different ways of slotting in some of the more computational kernels. So sometimes you use a preprocessor, if you've ever seen C, where you just put in, that gets a bit messy. These two C++ codes are using a lot of template metaprogramming type techniques, where you're actually doing templates and you're sort of getting that to write code, and a lot of the portability is hidden inside the templates. I mean, this is kind of really cool, but it means that only kind of, it's very hard for me to get graduate students to learn how to code in elite C++, because it's a kind of specialized skill, right? So I do think we should have codes at least for students to actually hack. And also the error messages are a bit nightmare as well. The US, they decided, the DOE said that they're building all these supercomputers. They said, well, actually, we should spend some money on the software as well, because we're spending £100 million on a supercomputer center. We want to make sure it's utilized, and also try and coordinate the different groups, because if each group has its own software specialist, it's better to kind of share and coordinate activity. So they've written all these libraries. So these are top-level codes. So these are the application codes. Below, this thing is a kind of matrix inversion library. This thing is linear algebra, like if you know BLAS or something like that, for specific things. Here's a sort of also like a BLAS-like QIOs for doing I/O. It's all kind of layered. This is linear algebra at the bottom. This is mesh patching. This is threads. So that's the good idea. Unfortunately, the downside of these things also makes the code slightly hard to compile, because whenever I compile a code, I have to get like 4 or 5 different libraries to work as well, and then the API changes, blah blah blah, and I do occasionally think I'm getting too old to do all this, but it's got to be done. Okay, just something about scaling. Okay, so some of these codes, Monte Carlo samples. Some jobs take like 24 hours to run on a large number of nodes. So efficiency is important. It's not the specialist myself. So this is GPUs. This is kind of graphics cards. Increasingly, some people are using that. This is only one of the plots I could actually find. So one way of doing efficiency is flops, which is floating point operations. A floating point operation is like 5 times 3. That's one floating point operation. And then you count the number of those and say how long it takes. That gives you the floating point operations. As you add in, this is the number of nodes. This is flops, teraflops is 10 to the 9. And you can see here that the performance scales up to about 96, and then kind of varies up. So GPUs are kind of quite powerful individual nodes. Other supercomputers have less powerful nodes, and then you can scale up to a larger number of smaller nodes. So you can scale a lot harder. But this is the kind of parts of the HPC game. Okay, a little bit about data. Okay, so that's some of the high performance stuff. So we're doing kind of Monte Carlo samples. One of the lowest things is a snapshot of the vacuum. Here I have some data. Here's the sort of 64 plus 192, 3 space dimensions, 1 time dimension. So an individual gauge configuration, 60 gigabytes. I've got 200 of them, about 3,000 gigabytes. This one, the smaller volumes, I've got 1,000 of those. On the high statistics that run about 4,000 gigabytes. That's it's the same To know what these numbers are, so obviously with the new PC, usually you get a disk of about 1 terabyte or 500 gigabytes. Our allocation on the Cambridge cluster is 400 terabytes. I'll talk about this a bit later. So this is not a huge mega big data application, but so this is like 400 disks. And but the thing is, when you're moving data around, sometimes data is generated on different supercomputers around the country. You've got to move things around over the network. It's slow. Copying stuff around, slow. So these are old figures. These are what I found. So CERN in 2013 had 100 petabytes. So a petabyte is 1,000 terabytes. Facebook had 100 petabytes. So it's small relative to that, but still, you know, a decent chunk of stuff. And I do spend, well, teaching this recently, a lot of time just moving data around, reformatting it, and yeah, in fact, somebody told me when I was at university, so, well, you know, you do physics and you're thinking about the great glory of the universe, and then the rest of the time you're just doing kind of not hard calculations, just doing kind of real, almost trivial stuff. And I'm meant to be doing stuff about dark matter. What I'm actually doing is moving 100 gigabytes of data from one computer to another and trying to get a code to compile for 3 days. That's life. Okay, so typically we don't use databases. Most of our files are binary files with metadata. Metadata is just information about the data. So the binary files is actually kind of physics things. These are kind of raw floating point numbers. Some of this is in text format. We used XML. This is, well, like tags and stuff. When I first used this, I thought it would be a great idea. But some of the graduate students, when I worked with the Liverpool, used to look at me and say, why are you punishing me using this horrible XML stuff? And yeah, well, okay. We have worked on, there were some international standards for XML schemas to make data more portable. This is like a stall at the moment. And this is more kind of jargon. Some of these things is network common data format. This is a way of storing data and metadata in the one file. It's a bit better than databases. But, okay, just some comments on data as well. So when I'm running on 4,000 cores, if I'm writing out 18 gigabytes of data, it can be expensive just to do parallel I/O, just to write stuff out. And I have been in situations where I've spent more time writing data out than I have done doing the calculation. You know, we do know about parallel I/O, and some applications have them, others don't. Just depends on who's done it. And also, some of the calculations, there's an issue with computation. So some of the key parts of the calculation are called core propagators. Doesn't really matter what they are. But I could sometimes, I recompute them sometimes rather than write them out to disk, because it's just a pain. It's more data. I've got to copy it around. And sometimes it's just better to do the calculation on my 4,000 cores, use it, create some other data, and then throw it away, rather than actually write it to disk with parallel I/O, move it around, store it, back it up, blah, blah, blah. Yeah, and all the issues is terabytes. So there's been situations, particularly for a conference, you've got your data on a disk with big terabytes. You know, it's okay to back up your PC. If it's a terabyte, it's 400 terabytes. It takes a while, even though we can cram backups. And what happens if it goes down? We had situations in the past, not recently, admittedly, these parallel things where the big data disk has been down for a month just before a conference. And you're going, oh, my talk is what's going to happen. For grand applications, when you write a grand application, you have to write how you supply a data management plan, how you store your data, how you look after it. This is part of the Research Council's things. Okay, there are packages to workflow, because my calculations, I pull in data from places, there's Monte Carlo samples, and there are, at the moment I have a bunch of Python scripts to do all this, and then my colleagues also have a bunch of Python scripts or Perl scripts, and we all have our own system for doing these things, and you think there must be a better, more systematic way of doing this, then we could all share effort rather than reinventing the wheel. And these things come under the idea of workflow, and if I had more time, perhaps I'd do that, but the trouble with these things is I'm not really paid to produce better software. I'm paid to produce physics papers, and I have to sort of, there's a kind of optimization strategy where if if I show my boss I've written this great software, they're just going to go, yeah, can we publish it in physical review letters? Great. And if not, then they tend to lose interest. Okay, so one time we did try to do this, which is, I did my best, man. I feel, I don't say bitter about this, but I'm a little bit bitter about it. So there's this idea of e-science, and okay, this is one of these things where when you get older, you remember things that happened 10 years ago that everyone's forgotten about, but I still remember. So this thing called e-science, the idea was a computational grid, and the idea was to do all this data handling where you have your code and you do some magic commands, the code would go off somewhere, run, it pull in your data, you get results back. If you think about it, wow, it's my dream. And they put a lot of money in it, it's right, 90 million, there's some number out, there's a huge amount of money put into it. And some of these things use Globus. And we did, when I was in the UK last time, we put a lot of work into it, partly because we've been using tape robots to store data, and somebody said a tape robot was, you write the data once, then read it never, because getting data off the tape robot used to be just as hard as, I mean, I talked to a vendor that said tape robots are a lot better, but they can be, you can write them and then just moving them around is difficult, and they're very slow, and blah, blah, blah. So we had this grid based on this Globus. So in that case, we had this idea, if you get the data, you didn't have to say where it was, you just have to say sort of the logical address. There was a database, the data was distributed around 4 sites in the UK, and there was kind of replica catalogs to make sure there's at least 2 copies everywhere. And so one of the issues, well, not everybody sort of bought into it. We put a lot of work into it, and there was a lot of community effort around the world. We had a grid, and then each country would have its own grid, so we could share data, because these gauge configurations are quite valuable, and once they're generated, you want to kind of maximize the amount of science produced, and it's not really fair on science. If somebody has a good idea, and they can't use these things, they don't have access to these snapshots of the vacuum, so they don't have access to this, but they have some good ideas, it's just, the data just sitting there not being used for anything. There may be some still grids available in Japan and continental Europe. All this kind of grid stuff kind of disappeared into the kind of cloud, and this Globus sort of sank away. And in fact, I'm just doing exactly the same thing I was doing 15 years ago. I'm moving things around, secure shell, running jobs with batch scripts. So all that money, nothing's changed. Okay, I might actually skip over the results for time. Okay, so I just want to show you some visualization type things. So most of the stuff we do is kind of raw number type things. People have tried to visualize these things as well. So this is kind of an action, so it's a 4-dimensional act. So an action is sort of the thing that gives you the dynamics. You have a 4-dimensional lattice. You sort of have to do cuts of 3-dimensional lattice to do visualization. And then the various colors sort of describe how the fields work. So this is, let me show. Okay, so this is an animated GIF. These actually come from a group in Australia. So what's happening here is you're looking at kind of charge density as you pull 2 quarks apart. There's a thing called confinement that when you pull quarks apart, you can never get an isolated quark. What actually happens is this kind of thing snaps, you get a pair of quarks, and you never get a free quark. And so this is just a way of kind of visualizing it. This is done by a group in Australia who are kind of famous for this. When Frank Wilczek got the Nobel Prize for inventing QCD, he showed some of the videos from this group. Unfortunately, there's no kind of open source packages to create these little videos from our data, and also there's some issues about how useful they are scientifically, the truth be told. I did find somebody did actually write a package, and I did actually download it. I did make one video using some technology called VTK video files. This package has not been touched for 10 years, so I can now actually do some of these simulations. The person who actually made it was a professor in computer science, and he's gone to work for SpaceX. And I'm like, man, some people have all the luck. Okay, so just some stuff about some hardware. So we have some clusters at the University of Plymouth. The system started in 2009, and we're now in the School of Engineering, Computing and Mathematics. So we have a small cluster. There's two, at the moment we have two clusters, both of which are around 50 nodes, fast interconnects. It's used for sort of particle physics and fluid simulations, and other people like statistics students. So I'm not involved with the hardware, but I tend to help users, graduate students get going, because it's a sort of Linux system, and all of everybody's experience with Linux. Yeah, it's going to have 250 terabytes. It's used for undergraduates and graduate students for projects. We also run physics projects. So it's useful for developing things, but also, like the fluids people, they use experience on that to write grant applications to use big machines, like in Edinburgh, that have a lot more cores. In the UK, what we use for our big resource is something called DIRAC, Distributed Research Using Advanced Computing, and it's the computing for particle physics and astronomy. There are 4 main facilities, one in Cambridge, one in Edinburgh, and other parts of Durham and Leicester. I've actually used Durham a little bit under friendly use time. So these have a lot more nodes, 11,000 nodes. Edinburgh is specially designed to do the really hardcore calculations of field lattice UCD to generate these gauge ensembles. Yeah, and some of these things are also, under the appropriate things, are available for industrial users if you have money. So the amount of money involved was 12 million, 15 million for the 2013. And we've had a refresh of some of the systems. We're now under DIRAC 2.5, and we're waiting for sort of DIRAC 3. The refresh, they kind of refreshed all the computers, but actually the amount of cycles didn't go up. So we had more computers, but the actual amount of resources didn't go up. And so this is just for particle physics. In like engineering and other types of physics, there's large machines in Edinburgh called Hector, and they're getting maybe another £50 million for an upgrade of their stuff. And there's also smaller machines around. We're hoping in Plymouth to refresh our machines and maybe put in more GPUs to do machine learning, and maybe get an upgrade to an M6 tier 2 situation. Okay, so why don't we use the grid? Not grid, why don't we use cloud computing? So when I talked to the head of DIRAC, he said whenever they give presentations to the government, they'd all say, why are you building your own computers and clusters? Why don't you just use the cloud? Just buy stuff from Amazon or Microsoft Azure. I mean, in proposals, we do cost these things, and it is cheaper to build university systems. This is part of that spec because we're using kind of free graduate student work and stuff like that. But there's issues about, you know, we do have our own kind of computing expertise. If we outsource all the stuff to big tech companies, we lose all that, and then we just lose all that expertise. There was talk about some pilot studies. So as I say, I mostly use to do computing. I mostly use kind of Linux and bash systems, and things have not really changed. I think we're going to have to start, just for training type things, is we're going to have to start using things like OpenStack, which is sort of cloud-based, free cloud-based systems, to make our supercomputers a bit more cloud-like, just to help users, because we are meant to be training graduate students and students to be data scientists, and so I think we should be doing things that is more industry-based. I mean, underlying the The cloud-based system is linked as well, so I've run things on that as well. Okay, so this is the end. So just tell the physics part is we understand 5% the energy of the universe very well. Unfortunately, 95% we don't understand at all. So, so some people have argued the way in which do science must change. All this stuff about hypothesis, we're just in the mode of us somehow. All these theoretical speculations, no experimental evidence. Is that really important? How could it be wrong? The theories are so beautiful. So one way, this thing I told you, doing this detailed comparison of theory and experiment, looking for virtual corrections, maybe a way to get up to larger energy scales, and it's what I'm spending my time doing. There's this experiment at Plymouth, big magnet. So in the next couple of years, there's a deviation. There's been deviation before. What typically happens is they go away, but maybe this time it won't go away, and this will be the start of something exciting, or it won't. And so what I say are these things. So we understand 5% of the universe. When you retire, the head of the department goes, when we hired Craig at Plymouth University of Plymouth, we understood 5% of the universe. He's retired because of his research. We now know 6% of the universe, and I'd be quite happy with that actually, and that's a lot better than a lot of other theorists. Okay, thank you for your attention.
Thanks, Greg. We have, if you're happy to, we've got time for a few questions around the room. If you do ask a question, would you mind repeating it so it's recorded? Any questions? I can start with one actually. So I noticed that there's in academia and the work you're doing, and certainly from my experience 20 years ago working in physics, we tended to write our own codes, and we didn't really rely so much then on open source libraries. Is that because the numerical quality of open source libraries isn't up to scratch? Is that the reasoning, or do you have any thoughts on that?
Okay, so the question is how much kind of open source generic libraries. Some things we definitely use, like Lars routines. There are some things we do use. Some software is kind of specialized. I told you the important kind of calculation runs is matrix conversion, and there are generic routines that will do that. But because our kind of applications are slightly specialized, we tend to roll our own. Some parts of the calculation we use open source codes, but also there's the kind of validation suite as well. Usually there's two different codes, we spend some time testing it. Yeah, I mean, just some of the applications are just too specialized, but things like some of the Python, like the data analysis things, are using scikit, stuff like that. So we do use some open source code.
Is it valid to have a concern about the numerical kind of stability and accuracy of the huge kind of ecosystem of open source numerical libraries? There's lots out there, and it seems like an easy thing just to pick and use them. But should one be thinking a little bit more carefully about how well tested they are and what the quality of the code should be inside those things?
Yeah, no, I mean, testing is... the answer is yes, we should be worried about testing. Normally, most calculations are done by 2 or 3 different groups, and then the results are compared, and then most people... I mean, there have been in the past occasional cases where one group is going to make a press release that they found some exciting new physics, and then they decide press release because there was a little error in the code. So, because we use model codes with different kind of code paths, you do have to compare the different codes. I mean, the worrying thing about it is because all this community stuff is very well, but it's all SciDAC, we're kind of reducing the number of codes. If we have 3 lattice calculations using one underlying library, if there's an error in that underlying library, it's going to percolate through 3 different calculations, so the error will propagate through. So you just kind of not hope that the calculations have to be done by multiple groups. And internally, we do checks. So we've written some new code with a graduate student, and we did one calculation with milk, and then we compared the results with the grid code, which is 8%.
Any other questions around the room?
Just wondering what you do to verify the randomness of the random numbers in your Monte Carlo loop. Do you have any sort of control to make sure you're truly random?
Yeah, I'm not an expert on the random numbers. I mean, people with small statistical systems, there's been issues when the random numbers repeat themselves, and that's been an issue. So there are experts who designed the random numbers to have huge periods so they don't repeat themselves. Do we check? I mean, there are specialized checks on random number generators. I mean, obviously, with things like Gaussian, you just check it, you fit a normal distribution to it. There are also kind of specialized checks for random numbers. I mean, there are people in the community who write specialized random numbers rather than just using system ones. Because there's definitely people written papers in the past statistical systems where the random number generators have not been good enough to produce correct results. And there's also an issue with, if you're running on multiple cores, they usually like to have a random number for each node, because as you change the number of nodes, if you don't do that, the numbers will change.
Good. Time for one or two more questions. Go ahead.
I was just wondering, because you mentioned the issues with moving code between computing clusters.
Yep.
I was wondering if you're using Kubernetes or Docker at all in that space. And also I was wondering about whether Apache Spark at all had been used, because you mentioned data portability and how difficult it was to move these huge data sets around, like within your cluster, whether you tried using those techniques.
So one of the things I like to do is like Spark or Hadoop type things. I just at the moment I just not have time to do it. I mean, we might start some not in Lattice QCD, in some student projects, and we had some talk with BT, who's providing me with a big enough data set. I mean, I know for the last Festival of Physics, the particle physics experiments, we had a Hadoop cluster. So we've not actually explored the technology. It could be other people in the community have. The issue I have occasionally used Docker. And yeah, I mean, one of the issues with it is just maybe not for performance, but I think actually for keeping a snapshot of the current version of the code. Because when we have like 4 or 5 different libraries, and I have one working version of the code, I sort of like to keep it at a reference scale. Because when things develops further on, it becomes useful to have a copy of that.
We found it really useful for being able to kind of like develop something on a local machine.
Sure.
And create a container that could then be moved into a cluster environment and get it have the same kind of results, if you know what I mean. It's the same Linux underlying.
Yeah, no. I mean, I certainly feel I should learn a bit more about Docker. I mean, one of my colleagues at Plymouth, he's tried to use Docker a little for some of the fluid simulations, and it turned out a bit harder. But it's something we're slightly aware of, but we should probably put a bit more effort into. Okay, thank you.
Very last quick question, if anyone's got one.
Can I ask something about this kind of the tenacity and the psychology of particle physicists? It feels like you appropriate this data, or you're given this data, or you collect this data, and you're looking at something. When do you stop looking at something? When do you think actually this data is a load of crap, there's nothing here, or do you have to sit the lot before you go, before you're satisfied? I mean, where does your kind of tenacity come from to keep going, looking for something when it might not be there?
Okay, so there's 3 communities. So what I'm doing, I mean, tenacity when you stop doing. What I do when I do a calculation, I'm computing something within a standard model, and if I have the errors now 5%, computing down to 1% is a completely valid thing. It may not give me what I want, but it is a completely valid thing. It's the same thing experimentally. If they're measuring something to 10% accuracy, then new things occur at 1% accuracy. That's, and if nothing occurs, it's still measurements, the way the measurements work, right? With the theorists doing things like supersymmetry, string theory, that gets more interesting. Because I'm pronouncing the name wrong, there's a blog called Sophie Hansfield who writes a blog, and she's sort of saying, why, and and there's another blog called Not Even Wrong, and all the string theorists and the supersymmetry people just say, we're never going to give up. And
because it feels like, granted I don't know much about this at all, but there's an assumption that something exists and then you look for it. Or is that a massive simplification?
No, I'm being kind of cruel and I'm being mean, and that's just the way it is. But the thing is, to get something to work, you have to believe. And, you know, because a lot of the time is, I've been to, if you talk to a professor, sometimes you talk to a professor, they'll go, that's a rubbish idea, Craig. 6 months later, one of their friends will say the same thing. And they'll go, that's quite a great idea. And you just have to believe what you do, because if you don't believe it, you can't get it to work. But it could be that some people are going to retire and they've made no experimental predictions. They've wasted their life. Oh, well, I mean, you know, they've written lots of papers, some of the things have been useful. And that's happened before. There's a thing called quaternions, which sometimes, this is a generalization of complex numbers invented by Hamilton. He spent 20 years working on this. It is useful a little bit in kind of computer graphics. I talked to a company about this recently, but he felt this was going to really radically change everything. And he spent 20 years of his life. It didn't radically change things, but it did have some impact. But so there is it's complicated. And the thing is, because they're a kind of self-supporting community, they're right, you can support yourself. And I mean, who can tell? I mean, research is all about betting, really. It could be that I've said all this and they'll say, this guy at Cornwall gave this talk and he really, I mean, Craig really complained about us and we were right all along, he was wrong. Research is all about betting at the end of the day. Could well be string theory, Susie's completely wrong. People have wasted 25 years of their life. That's their problem. I mean, there's issues whether we should fund it. But
could it be that, say, dark matter is basically not findable because the central property of dark matter is it not that it doesn't interact with normal matter except via gravitation?
Yeah, but that's sort of in the particle theory. I mean, some people think maybe you need to modify gravity. So there are a couple of alternative explanations. But at the end of the day, you need physics and experimental science. You need evidence. Without any evidence, you can tell.
Thank you very much, Craig. Wasn't that fantastic?